Hello students, today we are going to start another topic of our chapter gravitation. The objective of today's topic is to study about Kepler's laws of planetary motion. So the topic of the day is Kepler's laws of planetary motion. Kepler's first law of planetary motion is also called the law of orbits. According to the first law of Kepler, every planet moves in an elliptical orbit around the Sun being at one of the foci. So, according to the first law, all the planets revolve around the Sun in an elliptical orbit. Orbit means the path on which a planet revolves around the Sun, and Sun being at one of the foci. Unlike circle, ellipse has a different structure, so it has two diameters, and which is not diameters actually, which are called axes, minor axis and major axis. So it has two foci. So Sun is being at one of the foci. This is Sun, position of the Sun, and planet is revolving around the Sun in this orbit, which you can easily visualize here. So let's see the explanation of law of orbits. Planets move around the Sun in elliptical orbit. There are two foci for an ellipse. Sun remains at one of the focus. So this is the way how planets revolve around the Sun. Kepler's second law, which is also called the law of area. According to Kepler's law of area, the radius vector drawn from the Sun to a planet sweeps out equal areas in equal interval of time, which means the aerial velocity of radius vector is constant. So let's see what is the meaning of this law. According to this law, this white portion is called area swept by this planet. Alright. And according to Kepler's second law, the planet sweeps equal aerial velocity, means it travels equal area in equal interval of time. For this reason, the planet has to increase and decrease its speed. You can see here, at this position, the speed of planet is very slow, because it has to travel larger distance, it is farther from the Sun, and at this position it is nearer to the Sun. This point is called perihelion and this farther point is called aphelion. And when it reaches perihelion, due to strong gravitational pull, its speeds increases. So it covers larger linear distance, which results in larger area cover. On the other hand, when it is at the farther point, it travels a bit slower, so it covers less linear velocity, but we calculate the area travel at each interval will be equal. So this is the reason that aerial velocity of radius vector is constant. Let's see its explanation. According to the second law, the area swept by radius vector joining planet to Sun, so this is planet and this is Sun, is equal in equal interval of time, which results in velocity is greater when the planet is nearer to the Sun, it means at this point, than when it is farther away. When it is away from the Sun, its velocity decreases to cover equal area in equal interval of time. And area cover in a particular interval of time is called its aerial velocity. So throughout its revolution around the Sun, it sweeps equal aerial velocity. The third law, which is also called the harmonic law. According to the third law, the square of time period of revolution of a planet around the Sun is proportional to the cube of the semi-major axis of the ellipse. You can understand from this figure. Consider this is Sun and all these other dots are the planets which is revolving around the Sun in elliptical orbit. You can easily visualize here the planet which is nearer to the Sun means less radius, its time period is also less. Time period is less means it is moving faster. On the other hand, the planet which is farther from the sun means whose radius is more from the sun is slower, means its time period is more. We can conclude from this law that and the relationship between time period and radius can be mathematically represented as t square is directly proportional to r cube, where t is the time period of the planet and r is the distance of the planet from the sun, where r is the semi-major axis of the ellipse. So for explanation of the third law, we have to prove Kepler's third law of planetary motion. Let's prove the third law. Let us assume circular orbits. Let the planet of mass m revolve round in a circular orbit of radius r with a speed v. The force of attraction between sun and the planet, this is sun and these two are planets. The nearer planet covers the time period of planet which is nearer to the sun is less as compared to the time period of planet which is away from the sun. So the force of attraction between sun and the planet provides necessary centripetal force. So here the force of attraction between sun and planet is just because of the gravitational force of attraction, which is equal to g mm upon r square, and formula for centripetal force is mv square upon r. So these two are equal because gravitational force is providing centripetal force, so both are equal, where capital M is the mass of sun. From this equation we can cancel out 1 m, which is mass of the planet, and we can also cancel 1 r. So we are left with v square is equal to gm upon r. But we know that velocity is equal to 2 pi r divided by t. Actually, formula for velocity is distance upon time. As we are considering that orbit is circular, so distance traveled by planet is equal to 2 pi r divided by t, which is time period of the planet. So by putting this value of v here, we get 4 pi square r square divided by t square. 4 pi square r square divided by t square is equal to gm upon r. Taking t square on right hand side, and after solving it out we get t square is equal to 4 pi r cube divided by gm. Now students, you can see here this 4 is constant, pi is also constant, g which is universal gravitational constant which is also constant, capital M which is mass of sun, it is also constant. So this whole quantity is a constant. We can write this equation as t square is proportional to r cube, where 4 pi divided by gm is a constant. So in case of elliptical orbit, t square is directly proportional to a cube, where a is semi-major axis of the ellipse. So this is the proof of Kepler's third law of planetary motion. Let's solve an example. A Saturn year is 29.5 times the Earth year. How far is the Saturn from the Sun if the Earth is 1.50 into 10 raised to power 8 km away from the Sun? So we are given with time period of Saturn is equal to 2.9.5 times time period of Earth. Also, radius of Earth is 1.50 into 10 raised to power 8 km, and we have to find RS, means radius of Saturn. So let's see the solution. RS is equal to TS divided by TE whole raised to power 2 by 3 into RE. By putting the values of TS, TE which is equal to 1, and TS 29.5 and RE 1.5 into 10 to the power 8. And on solving we'll get 1.432 into 10 to the power 9 kilometer. Now you are able to answer all these questions. Question number 1. State and explain Kepler's laws of planetary motion. Question number 2. How will you deduce Kepler's third law from Newton's law of gravitation? And third question is a numerical. The distances of two planets from the Sun are 10 raised to the power 13 meter and 10 raised to the power 12 meter respectively. Calculate the ratio of time periods and the speed of the two planets. That's the end of the topic. Thank you.